All right, today we're going to cover Dalton's law of partial pressures, which is it's really very straightforward once you get past all the gobbledygook of what the actual words mean. So, partial pressure, Dalton's law says this, that the total pressure exerted by a mixture of gases is equal to Okay, is that the total pressure exerted by a mixture of gases is equal to the sum of the pressures exerted by the individual gases. All right, so we're going to look at this on the way we look at all of these on a particle basis. So we're going to have a whole bunch of flasks here. Okay. And in these flasks, we had some ducks. No. In these flasks, we have, in this one, we are going to have oxygen. And let's have, say, there's 5 parts oxygen in that particular flask. Okay, and the next one, or say this last one over here, is nitrogen. We have nitrogen down here, and there's, let's see, there's 15. All right, so we're going to call this 5 parts, or 5 moles, or 5 millimoles, or whatever. This is going to be 15 parts to it. Right, so this has 5 times the number of particles that this oxygen does, right? Now, everything we've learned so far, that if this is the same flask and it's the same volume and the same temperature, that how are the pressures of these two things going to compare? Okay, so if this has 5 moles and this is 15 moles, then the pressure inside this flask would be not just greater, but 3 times greater, right? If we have triple the moles, we're going to have triple the pressure, right? If it's the same flask and same volume, same temperature. Okay. Then we have some CO2 in this one. Okay, and this is going to have 2 molecules of CO2 in it. Okay. All right. And then this is going to have a whole bunch of others. So this is, we'll just call this air. All right. Or just other forms. We'll not call it, not air. Let's call it water. And there are 3 molecules of water in that. Okay, are we cool here? All right. So we have these, we could have mutual proportions of moles. And I don't want you to worry about that. But here, what I want you to imagine is we take all of these molecules now. In fact, I want to do this a little differently. I'm going to make these different colors. Call that green. And oxygen, because oxygen's always red. And we're going to make water blue. Okay. So now we're going to take this flask, but we're going to cram all of these moles into the same flask, right? So We create the flask. We want it the same size. Roughly. Okay, and this is going to be our oxygen and our CO2 and our H2O and our nitrogen. All right, and we're going to, into that flask, we're going to make put all of those molecules into that flask. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And 1, 2, 3 waters. And 1, 2 carbon dioxides. And 1, 2, 3, 4, 5 oxygens. Okay. We have a lot more molecules in that flask, don't we? Yeah? Okay. If I told you that the pressure exerted in this carbon dioxide was 0.2 atmospheres, what do you think the pressure in this one would be? Right? So if this one is 0.2, then this one would be 0.3, right? How about this one over here? This one would be 0.5. And how about this one over here? This would be 1.5. Right? So now, if we put all of these moles into the same flask, what do you think our new pressure would be? Okay. How do we get 2.5? We add them all up, right? So it would be the pressure of the O2 plus the pressure of the CO2 plus the pressure of the H2O. Oh. Okay. Plus the pressure of the N2. Okay, if we add them all together, so it'd be 0.5 plus 0.2 plus 0.3 plus 1.5. All these are going to equal 2.5 atmospheres. Okay. The fact that this is correct is Dalton's partial law of pressures. Okay. That you take the individual pressures of the gases, and if you combine them together, that makes the total pressure of all of the gases combined. But we can use this concept to determine what the pressure of a missing gas. So let's say we measure the pressure of this, and we measure it to be 2.5, right? And we know that 1.5 of it comes from nitrogen, 0.2 of it comes from carbon dioxide, right? And 0.3 comes from H2O. We can determine that the rest of it comes from the gas that's left, or the oxygen in this case. Okay, that is Dalton's law. Okay, now we have a fancier way of writing it, and it's this line right here. Okay, this equals the total pressure, and so it's the general equation is going to be that the total pressure equals the pressure from the first one plus the pressure from the second one plus the pressure from the third one plus and so on. Or if you really want to get fancy, it's the sum, okay, or K equals 1 to N, okay, which is really ugly. But the idea is that's the summation notation, that you add for however many pressures, I'll write it bigger. You guys have seen this symbol before? Sigma? It means sum. Okay. Okay, so this is the first one. That's however many you have. So you have 5 gases, you'd stop at 5 of that pressure. So your pressure of your first one, plus your pressure of your second one, plus your pressure of your third one, all the way to N is the sum of all your pressures. Okay, this is just the fancy math way of writing it. If you write it like this or understand it like this, that's fine too. All right, that's Dalton's law of partial pressures. Now, we need to change gears a little bit because it's a slightly different topic, and this one is diffusion. Diffusion. Okay. You guys ever dealt with it? We just had Easter. Have you guys ever gone out, a couple weeks after Easter and discovered that you didn't find all the eggs?
Yes, I've done that.
Okay. And then, of course, Shubin being Shubin, went out there and cracked the egg, right? Okay. And when he cracked the egg, okay, it emitted an odor. Such a glorious, sulfurous odor. Okay. That now when he cracked the egg, he would be the only person to smell it at first, yes?
Yeah.
But then, as time went on, okay, the smell would spread. And other people would go out into the backyard eventually and say, "Woo! Shubin, what did you do in the backyard?" "I cracked an egg, honest." "Sure you did." Okay, that's the discussion you get. Now, why is it that when when Shubin here, okay, is right next to the egg, okay, he smells it first. Okay, but Joseph, who's on the other side of the yard, he doesn't smell it yet. Why?
Because the scent hasn't traveled yet.
Okay, what's that? Okay, the scent hasn't traveled yet. Now, I happen to have in my drawer right here a leftover Easter egg. Oh, what do you have? I'm lying to you. I don't have one. What? Oh, you have something smelly? Sure, totally. Let's try that. Come here. Yeah. Well, not to use, but okay. So the smell doesn't travel. Joseph doesn't smell it immediately. It takes some time for it to travel from here to Joseph, right? Okay. Does it require wind?
No.
Okay. So if I open this, I guess it's particularly smelly. Okay, so if flee, be free. Okay, so I have let it out. I have let the genie out of the bottle. Okay, and pretty soon you should be able to detect the genie. Now, nothing. I was totally joking about having a rotten egg. No, it's something else that made the smell. Okay. Now, I usually talk about this in different ways, but I'm recording it, so I'm not going to refer to, if somebody farts across the room, what, the people right next to them are the ones that get to experience it first, but then it eventually, okay. But there's two factors at play. One, Joseph doesn't get to smell it right away. Okay. Joseph doesn't have the opportunity to share the aroma with Shubin quite yet, because he's some distance away. However, When he does get the opportunity, how intense do you think the smell would be? Not as much. Okay, why not? Okay, well, one more time, Nick.
The particles that were causing the smell dispersed more throughout the air.
They've dispersed. Do these particles travel? Are they directional? Do they go straight at Joseph? No. Right.
They disperse in opposite directions. It's all about your lexicon. Got you.
Because of the random motion of molecules. Okay, because of the random motion of molecules, they just move in random direction. They bump into each other. Okay, a concentrated sample of gas will distribute and disperse from its source until it is evenly distributed. So, when Shubin, sitting over there in the corner, decides to crack an egg, okay, over in the corner, it stays over there, okay, but it will that smell will randomly distribute throughout the classroom. Okay. However, those of us that are further away, lucky me, we experience a much less intense because the molecules have spread out and they've dispersed very evenly throughout the room. Okay. The way they do that is just through the random motion of the molecules. Okay, so they go from a concentrated region over by Shub, over to us, or those of us at the outside of the classroom, and all the molecules, because we're in a container, they will eventually move randomly until it is evenly distributed throughout the classroom. At that point, okay, it is probably dispersed to a point where it's barely even detectable. Okay, that's how smells happen. Now, this is a bit tougher of a draw. Don't attempt to draw this until I finish so you can see what I'm doing. Okay. Okay. These are all connected with this tube that touches all of them. Okay, we have a flask of gas here and a flask of gas here. Okay. If I were to open all of these valves and let it sit for a while, what would it look like after the while? Okay, they'd all be in the middle with nothing here?
No. There'd be a little bit of everything everywhere.
a little bit of everything everywhere? How would you draw that? Okay. So, these molecules, you're right. These molecules would, because of the random motion molecules, they would start working their way up through the tubes. Okay, and the red ones would wind up coming this way and down here, and the blue ones would wind up coming this way and over here, until you would have an even distribution of all of the molecules throughout the entire apparatus. That make sense?
Yeah.
Okay. That is the idea of diffusion. Okay. Now, one of the more disgusting ideas about diffusion is that when somebody lets one go, one of the things that you are smelling, and the reason it smells like poo, is because you are actually inhaling poo. That's what smells are. Smells are actual particles of the thing that you're smelling. If you smell apple, you're inhaling apple. Well, you smell poo, guess what? Okay. If you step in something out in the yard and you catch a whiff of it, guess what you've disturbed and kicked up into the air so that your nostrils can detect it. Okay. So, on that thought, that is diffusion. That is Dalton's law of partial pressures. That is diffusion, and we're done.